All right, we are supposed to be live here, but I am not seeing the live stream come up on my computer yet. There we are. All right, and I can hear myself. I got internet in my workshop, so I can actually monitor your comments over here while we're doing the live stream today. I don't have to be walking back up to my phone again. So welcome, those of you who are already here. This is the second Patreon live stream, and I actually have some work to do today. There's a few things I want to do. So I am, first of all, going to be working on, I really need to figure out how I'm going to film this video about phase change materials that I have been working on. I need to figure out my intro, just kind of how I want to present it, because I've come up with a very useful material, I think, for personal cooling and potentially the temperature regulation of buildings. I need to come up with exactly how I want to present this. And the other thing that I'm going to be doing today, probably on this live stream, is testing the heat capacity of the phase change material that I have come up with. I've been working off of a paper that did most of the work for coming up with these materials, and then I put my own little twist on it. So it's not a completely original material, but it's one that is not well known, and it has the potential to keep you cool all throughout the day with little or no electricity. It's pretty awesome. What I want to do in this live stream, first of all, I can answer your questions because, well, this is not an official Nighthawk and Light video. It's going to be just a casual thing, and I'm not going to put a ton of effort into making this a professional presentation here. But I do want to be able to answer your questions while I'm getting some work done, and hopefully this is something that I can keep doing to give you guys a little bit more reward for supporting me on Patreon. I really appreciate that. And I'd love to be able to offer you guys something in return for that, even though I know many of you are just doing it to support my work. I really want to give something in return, and I want to practice my camera presence live. I want to be able to make videos like this in an entertaining and engaging way where, well, this is something that we can do regularly. All right, I'm rambling now. So what I'm working on here, I've went out and I've got some styrofoam cups, and I'm heating up some water in this pot. And what I've been doing, if you missed the previous live stream, I've come up with this phase change material, which holds on to a ton of heat. It's basically like an ice pack, but it's a totally different material than water ice. This is a salt mixture, primarily sodium sulfate, and it solidifies it's starting at around room temperature and going all the way down below the freezing point of water. And so you get this wide range of heat absorption where this is like an ice pack that stays at, well, you can explain, I guess if you had a normal ice pack, you're very used to feeling that ice pack be cold at first, and then all of a sudden it basically loses its cooling potential and it shoots right up to your body temperature really quickly. This doesn't do that. It will stay as cold as ice for as long as ice would normally, but then as it starts to gradually get warmer, it doesn't do so quickly, and it'll actually stay below room temperature for hours and hours and hours, even on a very hot day. Yesterday, I've been working on making a seat cushion out of this stuff, and I sat on a lawn chair throughout most of the day yesterday in 85-degree Fahrenheit weather. Those of you outside of the US, I don't know what that converts to in Celsius, but it's a pretty warm day. It's probably like almost 30 degrees Celsius. And a seat cushion that I made from this stuff lasted throughout the entire day, keeping me cool without actually having it in the refrigerator at night. I just had it charging up, cooling down to below room temperature in the basement of my house. So it's a pretty amazing material to be able to keep you cool on a hot day without needing electricity. All you need is a cool place to store it. And it can actually also be cooled down by radiative cooling at night. All right, let's see who we got on here. Jonathan, welcome. Alvaro, Costa Rica, awesome. Thanks for stopping in, guys, and thank you so much for supporting me on Patreon. I'm actually meeting with a local editor tomorrow. I've had editors already that I've found on the internet for making the shorts that are posted to this channel. Actually, if you're watching this live stream, It's on my Nighthawk and Light Shorts channel. And so I've had editors making those shorts for me for some time. I am sort of happy with their work, but not quite enough to trust them to work on my long form videos. Well, I'm meeting with a local editor tomorrow that hopefully I will trust. And it would be because of your Patreon support. Basically, all the money that I would get for these videos from Patreon would go into paying that editor. And what that would do is cut down the time I spend on these videos by 2 or 3 weeks per video. So hopefully that means I create videos 2 or 3 weeks faster, more frequently. So thank you guys so much for supporting this channel, and hopefully it's about to pay off really well with a lot more frequent videos. I keep interrupting myself. So I'm trying to get this water up to boiling so that we have a warm temperature of water, and then we're going to pile a little bit of my phase change material and a little bit of ice into these tiny little plastic bags. I'm going to weigh these very carefully, and we're going to cover these foam cups so that the heat is really sealed in. Then we'll drop the phase change material into the cup and measure what the temperature change is of the water. See how cold the water, the near boiling point water, will become from the known quantity of the phase change material. And by comparing that to a similar quantity of ice, actually it doesn't even matter that it's a similar quantity, you just plug it into an equation and that accounts for that. You actually find out how much energy this phase change material is able to store. And by my earlier tests, the tests that I've done so far, it is much more than water ice, which is really weird, because no one says it is. This is a phase change material that has been messed with by some people before. I don't think quite in this configuration, but all of the papers that I've read say that this stuff has cooling potential that is way less than ice, about 2/3 of normal water ice. My experience has been that this is way better. Like, I've stuck this in my freezer along with a sample of ice, put it into a similar environment in heated water, and the ice melts way faster, and there's actually no point on my little temperature logging thermometer where the ice is colder than my phase change material. I'm going to have to present this in the full video for the most part. I can't spoil it too much. What I'm going to do here is I will scoop out some ice out of a cooler I have down here and get my samples measured and then cooling down to ice water temperature while this water is boiling. How's the audio, guys? Can you hear me all right? I have my microphone's a little bit further away than it was last time because it's now mounted to the same stand as my camera, which is also kind of far away. Audio is great. Thank you. Can you think of anything that would explain the difference between your observations and the papers you've read? I can. So I'm starting to get to the point where I'm going to rush this video out a little bit. I mean, at a certain point, I just have to start filming this project because I've already discovered some stuff that I think is going to be useful to people, even though I haven't. I mean, I could spend all year making investigations into phase change materials, and I don't really want to do that. But my suspicions, without being able to well research, is that we're dealing with, so what I have in this container is sodium sulfate and table salt. So 2 different salts that have different freezing points. And what happens, I think, with these, it's called a eukectic material. The 2 salts form like a crystal structure that is not, that is like a mixture of both salt structures combined. And I think what's happening is that we're getting a continuum of freezing points throughout this mixture. So when we get down to room temp, for example, this mixture in front of me has not been in a freezer. It's just been in my workshop overnight. And there's a lot of crystals in here. A lot of stuff is frozen in this solution, which means that the phase change has already started. But at the same time, it's still quite liquidy. And so there's a lot of stuff that has not frozen. And so I think what's happening is we're getting an initial freeze with the components of this mixture that freeze at the warmest temperature, and as you continue to cool this down, you're getting different crystal structures that progressively freeze in steps, and so you end up with just a continuous phase change instead of If I could show you on my computer, I can't really do this, but I have some temperature data from when I have logged the freezing point of this material versus ice. And ice, it goes down like this. It goes down as it's freezing, and then it stops, and it just goes in a straight line for a really long time at 32 degrees Fahrenheit, 0 degrees Celsius, the freezing point of water. Until the ice is fully frozen, until all of that water is converted into ice, it doesn't move off of that temperature. So it just goes level, and then when everything freezes, suddenly it goes down again. Well, this definitely has a freezing point because it turns from liquid into solid, but you don't get that leveling off like that and then another drop down. It's actually just a slow, gradual drop down the entire way, which is really weird. And I've not seen any papers reporting on material behavior like this. Usually in a material that has a freezing point, you go downhill as it's cooling, and then it levels off at that freezing point, and then it continues to go down. That's what I was expecting with this material. It's not at all what I've seen. It's a really gradual slope. And so what I'm thinking is that because of that gradual slope, we have a mixture of different freezing points in the solution. And because when I'm warming them up, how do I put this? So for ice, it tends to warm up really quickly outdoors in like the summertime when it's like 40 degrees Celsius, like 110 degrees Fahrenheit. That ice is going to melt really quickly because the difference in temperature between the freezing point of ice and the air temperature is really extreme. With something like this, the freezing point is closer to that high temperature. And so the difference between them means less heat is transferred as rapidly. And so that slows the progression. So that's one option as to why this is slower to warm up. Another option, and then that doesn't really explain everything, but another option would be like the thermal conductivity of the solution. I don't think that's it. I've tested different shapes of containers that would have different levels of insulative value if the heat conductivity of the material was bad. I've tested it in a really narrow water bottle, which is half the diameter of a beaker like this. And if the slower temperature rise were just due to poor thermal conduction in this material, then the narrow bottle should have warmed up much faster because the thermometer doesn't have as much material surrounding it, which would be insulating it from the change in temperature. So I don't think that's it. I have no idea, I guess, is where I'm getting at. I have no idea why the other thing is this maybe is just it has a better heat capacity against all papers that I've found. Maybe it's just better. And maybe the reason is because it has that mixture of freezing points in the solution. The various papers are probably just measuring one particular crystal structure to find out its heat capacity rather than the whole continuum that I'm getting. And so maybe there's something in this that is a particularly good heat storage form of this material. Yeah, it's complicated. It's complicated. I think we're getting like some of the crystallization happening probably pushes various ratios of the salt mixtures out of the crystal structure so that the remaining liquid in the solution is a different mix that then freezes at a different temperature than the first stages of crystallization. I don't know. Yeah. A lot of these mixtures have an issue with settling out. Did you hear me when I walked away? So a lot of these, they have an issue with settling out where the crystallization happens throughout the entire solution, but because the crystals are heavier than the liquid, they sink to the bottom. And then you have kind of a problem because when this goes to dissolve again, you're going to get a denser solution in the bottom, a more concentrated salt solution, and you won't have the right ratio of water to salt in either area of these containers. And that's a real problem if you're not actually agitating these regularly. If you were trying to use them, say, to cool a building down, you don't want to have to go up into your attic and like stir these containers every day between the freeze-thaw cycles in order to get the proper mixture back again. And I've been able to correct that in two ways. First of all, adding the mixture of salts tends to make the crystals more spidery and less like a dense structure that sinks to the bottom. And so they just naturally kind of distribute themselves throughout the entire container a little bit better. But then the other way is to add a gel to the solution. So this is like a really thick jelly, and it's worked perfectly. So all in all, there's some really neat things, some neat improvements to phase change materials that I think I'll be able to present in this video. Cool. Okay. All right. So in order to find out the heat capacity of my materials, the first step is to weigh out some samples. So what I will start with, all right, I'm going to put one of these little baggies that I'll be using as my sample baggies on the scale here. And I'll start with my phase change material. So let's zero the scale with one of these baggies on here, and then just scoop out kind of an arbitrary amount into one of these bags. I think that the larger the sample is that I use, the more accurate my reading will be, because we won't need to use as many decimal places in our units in order to see an accurate result. So if I can fill this baggie pretty full, I can get a little more in there. I'm pretty happy that that I can live stream. I'm just off my phone like this. I've always wanted to do this. I'm not brave enough, I guess, to do it on the main channel at this point, and you know, I like it being a Patreon perk, but I'm really glad that I can do this. Okay, so the sample of my phase change material weighs 26.99 grams. So I'll just say 27 grams even. And I will record that, and then we will put this in the ice water to cool down. Where's my thermometer? I shouldn't clap, sorry about that. So Celsius, this should be about 0 degrees Celsius. 0.8. All right, 0.8 is pretty close. Well, hopefully these baggies are fairly leak proof. Get some magnets. Get some magnets to hold the edge of the sample bag just out of the water here. There we go. And I'll let that sit there while I weigh out. Well, I want to weigh out some ice actually, but I think what I'll do for the ice is I will wait until I'm right before I'm ready to to fill the cups with warm water and actually begin the measurement, because the ice is obviously going to be the same temperature as the sample if I just take it out of this container. So we'll leave that to sit. Let's see what the water temperature is in here. Currently at 63 degrees Celsius. I don't need to exactly get it quite to boiling. It's kind of a tall order to boil. This is about half full. Kind of a tall order to boil that container of water on that little electric burner. But I do want to make sure that it's warm enough to actually fully melt the phase change material. I don't really have much doubt that it's going to be able to melt the ice, but if it doesn't melt the phase change material, then I won't get a complete measurement. And the other thing I kind of want to do is I want to test a little piece of a brick through the same methods. And in that way, well, mostly that's just for vanity, because cement is not it doesn't have a lot of heat capacity. It has less than half of the heat capacity of water. And so I know I already know if my material beats out water, that it definitely beats out brick. But I figured it would be a really cool thumbnail to be able to hold up just like a little beaker of this stuff next to a whole pile of cinder blocks, and like, I don't know, have like an arrow pointing at the cinder blocks or something from here and be like, this has more heat capacity than this whole pile of cinder blocks, which I think is going to be very true. So I don't know. You got to do a little bit of clickbait. I mean, it's true, but it's, you know, it's clickbait in the sense that it's not exactly a fair comparison. If I do my thumbnail like that. Can I even get one of these stones in this bag? I only want to put it in there because it's because if it gets wet, then the water that it absorbs is going to throw off the measurement. 15 grams. Mass of the concrete is 15 grams. Excuse me. All right. And I will throw this in my ice as well. Yeah, we'll see. Maybe I will, maybe I'll use some of the footage that is captured by the live stream in the main channel video. Yeah. I was thinking about future topics for these live streams, and there might be a few things that I'm able to do on these that I've wanted to make a full video out of for a long time, but they're just not, I don't think that they would perform as well as I would have to expect for the main channel. Things like just playing with my Starlight material, the Starlight analog that I made in earlier videos, just kind of doing like the egg test live. I hope all of you have seen my videos on Starlight. That's one of some of the best videos that I've made, I think. I don't know. I guess I've made some good ones, but yeah, just using some of that fireproof putty, intumescent putty on camera to see, like, can an egg actually survive? Like, how long can an egg survive under a propane torch before starting to become cooked under that Starlight material? I think that would be a pretty fun live stream, just to do a whole bunch of tests with that. And yeah, so that's one option. I also have a video that I've been meaning to make for a long time about like basically danger, things that are actually dangerous versus those that have the appearance of danger. Excuse me, it's starting to get warm in my barn. There's a lot of things that I've done on this channel where people freak out in the comments about how dangerous it is. And the reality is I've never injured myself in any significant way making all the videos I do, because my aim in a lot of my projects, at least I guess it's been a while since I've done one that's significantly dangerous or looks dangerous, but my goal in a lot of them has been to have the appearance of danger, make it look really good on camera, but not actually be in any danger. And the difference in that is extreme. Stuff that does not look dangerous is the stuff I've hurt myself the most severely with. I mean, there was a video that I made making a giant pendulum wave, where you see like patterns come out in a series of pendulums as they progress over time. And I injured myself pretty badly in that video, cutting pieces of string with a razor blade. And I slipped and cut myself. I was working on the video too late into the night. I was getting tired and should have stopped filming, but I wanted to do like a glow-in-the-dark shot, and I wanted it to be nighttime while I did that. So I was just working too long and too hard, slipped with a razor blade, and cut myself pretty badly. I've never done anything like that, like with the experiments with fire that I've done. A lot of the stuff that I've done with that looks dangerous, but really isn't. Another one is I have a wood stove back here that I heat the shop with sometimes. And 2 winters ago, it gets really dry when you use a wood stove to heat a building, because it's heating the air but not adding any humidity back into it. And so I'll put a pot of water on the stove, or sometimes I'll just throw snow on top. Well, I had the stove really cooking really hot, and I dropped a snowball on top, and it caused not a steam explosion, but just a huge amount of steam to come off immediately at super high temperatures, and it burned the skin all up and down my arm. Dropping a snowball, onto a wood stove. You would not think that would be dangerous. It doesn't have the appearance of danger, but it's much more dangerous than a lot of the seemingly dangerous stuff I've done on this channel. All right. Let's see what temperature we're at here. We are at 72 degrees Celsius. All right, let me get out. I got these neat little temperature logging thermometers, which have a little, they're actually really nice. They're like 45 bucks, not a sponsor or anything, called Eli Tech thermometers. And the only downside with them is you have to plug them into your computer every time you want to end a recording with the thermometers or start a new one. You have to reset it on the computer. But otherwise, besides that, it comes with really nice software, and I've needed one of these for a really long time in order to test like my my radiative cooling coatings. I want to be able to test those throughout the entire course of a day and night cycle, and be able to read off a graph what the temperature did when it was in full sunlight versus at nighttime. And these are the kind of things I need for that. I have another. I mentioned a long time ago in a video that I wanted to actually put my radiative cooling coatings or cooling panels onto a little shed I have in the backyard, and then test their performance on an actual small structure. Well, again, I need to be able to log the temperatures over a long period of time in order to see that. And so these ended up being necessary to test the cooling capability of these PCMs, phase change materials, and so I bought a few. Actually, I didn't know that these existed until watching a Tech Ingredients video. You guys follow Tech Ingredients? It's a great channel if you don't. Yeah, he was, I forget what he was doing. Maybe seeing what would happen if you turned your air conditioning. I think he was using his house as a thermal battery, basically turning his air conditioning on at night when electricity is cheapest and most abundant, so that it is cold throughout the rest of the day without having to kick on his AC during the high price periods of electricity and high demand during daytime. And so he bought a bunch of these temperature loggers to see how that actually performed. I think that's what he used them for. Maybe he's done a number of different things. But anyway, I'm warming up because these have they have an oil capsule on the end of the probes to make sure that the heat is read very evenly and that the temperature doesn't swing back and forth every time the wind blows. And so I want to warm those capsules up to the temperature of the water that we will be using for this test. And in the meantime, let's get out some of my styrofoam cups here. This one I already kind of got. I guess it's... I'll save this one. I got that one wet. And there's not much water in it, but I don't need to be throwing off the test with some unnecessary variable. So what I am going to do, got my samples in there. I think that I'm going to do this one at a time. So I'm not going to, well, I have 3 samples that I want to test. I want to test a weight of ice. I want to compare my PCM to ice. And I also have that piece of cement in this solution. I don't want to use, I can't really measure all 3 of them at the same time unless I also use my second thermometer. So I think I'll just do 2 at a time. I'll do the ice and I'll do my my sample of my phase change material. I want to make sure that this actually is in the center of the solution. How do I do that? Because I also had it held to the side with these magnets. You know what? I don't think water is going to leak into here, and if it does, I'll be able to see it on top of this sample. So I'm just going to put this right in the middle. Yeah, it's sitting on the ice so that the edge of the bag is actually above the water, and that should be pretty good. I need to let that sit in there for a good long while, because just like it takes a long time for a phase change material to warm up, it takes a long time for it to cool down because it's holding on to a lot of heat. And that's what it's getting rid of throughout the course of cooling down, so that when you take it out, it remains as an ice pack for a really long time. I have come up with a few uses for this already. The simplest that I've come up with, I mentioned this at the start of the stream, is a seat cushion. And that it was just kind of like an afterthought. I made a really big I basically soaked a towel in this phase change material and put it inside of a plastic bag and then threw it in my freezer. And then I was planning on using this as I was contacted by a paramedic some time ago who wanted to come up with some kind of blanket that they could put on people with heat stroke that would cool them down even on high humidity days when you can't rely on a wet blanket to actually cool anybody, to actually cool anybody down because the humidity is too high for evaporative cooling. And so my intention was to make a blanket that would actually cool people down. Well, it turns out you fold this thing up and set it on a chair and it'll keep you cold all day long. It's pretty awesome, and you could easily see that being done inside the cab of like a delivery truck where they have to have their door open and close all the time, or a mail truck where the window has to be down the whole time and you can't really rely on the AC to keep you cool. That could be a great way to help people just prevent heat stroke. Just having a seat cushion. At first I was thinking, so the other option are these vests that you can get on eBay and Amazon, and it's a vest with a bunch of internal pockets, and they look a little bit goofy. I don't like the look of these, and the dumbest thing about them is all of them online. When you go looking for these vests that are meant to have ice packs in the internal pockets to keep you cool, they're all a dark color. They're all blue. I guess for marketing reasons, it's a cold vest, it should be blue. But that's really stupid because blue is a dark color and it absorbs a ton of sunlight. And so while you're wearing this dark blue vest around with your ice packs, the sun is absorbing into the vest, melting your ice packs, and where there are no ice packs, like on your shoulders, it's just warming you up. This should be reflective, like aluminized mylar. It should be like tinfoil, a perfect mirror, or it should be really bright white. And you just can't find a bright white vest like this. And so it's unfortunate. I mean, it's no problem if you wear it under your clothes, but then when you go to actually change out the ice packs, you got to take your shirt off in order to change the ice packs out. The one good thing that these vests can do that it turns out is kind of necessary, because I was thinking you could actually just take laundry bags. They're like mesh bags with a zipper on them, and you could just sew those to the inside of any clothing, and then you'd have pockets to put ice packs into. Well, the nice thing about these vests that are actually made for cooling you down is they have straps on the sides that you can tighten. Because if you don't have your ice packs actually firmly pressed against your skin, then you're not getting their full cooling effect, and you're getting air circulation under the ice packs that is just warming them up faster than normal. But it is, anyway, all that to say that you could put my phase change material into homemade ice packs in one of these vests, and that was my initial thought for keeping you cool. But it could be much easier for those people who sit on the job, who are delivery drivers, or working on an unair conditioned factory or something like that, just to have an ice pack on their chair, and that's just so much simpler. For people that actually have to do a lot of running around, these could still be a good option. They're like $20 online. Yeah, I just wish they made them in a lighter color so you weren't absorbing all that unnecessary solar radiation. All right, let's check comments over here. I'd love to find a material that reflects most light and passes infrared. There are actually materials that do that. What are they? Reflects most light and passes infrared. Whatever they make lenses for thermal cameras out of has got to be that kind of material. I want to say probably you could do very thin, like molecularly thin layers of various metals. Sputtering is what you would call that, where you take an electric charge in a high vacuum and you electrically deposit a very fine metal film onto a surface, and you can get all kinds of properties out of that. You could make one of those films that passes most IR light, but then also reflects a lot of visible light. Another option that would work for that actually is acrylic. Very pure acrylic. You wouldn't be able to use, for my radiative cooling paint, I use store-bought acrylic. It's optics, or Plaskolite Optics brand acrylic is what I use for my infrared cooling paint, and that actually has most acrylic that you like, acrylic windows actually has something that absorbs infrared in the material, and so infrared won't pass through the acrylic because it has a pigment in there that is meant to absorb it. However, if you get pure acrylic without any additives, which you can get acrylic beads, powder online, it is transparent to almost all infrared light. And then you use the same method that I do for my infrared cooling paint, where you add a little bit of water to dissolved acrylic, and then when it solidifies, you get a snow scattering effect. So that's another way that you could reflect most visible light and pass infrared. Yeah, water cooling system on the seat for USPS. Definitely. I mean, yeah. Here's the thing though, with water cooling stuff. I mean, yeah, you'd have to go buy a bag of ice or whatever to throw in your cooler with your water to circulate that and cool your seat. With these PCMs, so I used this stuff in my little seat cushion setup that I described earlier without actually having it in the freezer or refrigerator. I just had it indoors because it has a high freezing point at about room temperature, 70 degrees Fahrenheit, whatever that is in Celsius, I don't know. Because it has that high freezing temperature, it can actually get a lot of cooling potential just sitting at room temperature indoors. And then when you bring it outside, it's basically a 70 degree Fahrenheit surface, and it stays that way for a really long time. Now, 70 degrees may not sound very cold. Let me just see what that is. What is 70 degrees Fahrenheit in Celsius? 70 F2C, 21 degrees Celsius. So it's not incredibly cold, but if you've ever been in a swimming pool that is 70 degrees or 21 degrees Celsius, that's pretty chilly water. That will cool you down on a hot day, a 70-degree swimming pool. And that's basically what a PCM like this feels like if you have good thermal contact with it. It's like that part of your body is touching, very cold pool water, and that's enough to cool you down, even though it's not as cold as something like an ice pack. And it's because of that small temperature differential. It's room temp instead of like the temperature of ice, which is much colder than room temp. That small temperature differential means it lasts way longer. So that's one of the reasons why it's useful and why it can last. I mean, it lasted for me hours and hours, just having been inside my house for a little while. It can get even colder if you take it down into a basement and put it on the floor where the temperature is more like 60 degrees Fahrenheit. Yeah, so it's awesome. It's definitely it's a material that could be useful even if you have no electricity. You could dig a hole in the ground, or even if you were in a town with a well or something. I guess you'd have to be careful not to. I've been in towns with that their only water supply is a well and a bucket, by the way. And if you were in a town like that, you could just lower a container full of something made like this down into the well, where it's like 50 degrees Fahrenheit year round, and it would chill down enough to keep you cool throughout the entire day. If you left it in there it cools down extremely quickly in reality. So you only would need it down there for 20 minutes to get a couple hours of cooling out of it. It's pretty amazing stuff. All right, are we ready here? I think we gotta be. So what I am going to do, I already have my my heat calculation over here that I'm going to be using, the equation. I'm going to be using basically a specific heat equation, which is for measuring the heat capacity of materials, but I'm going to be doing it with, we're going to be putting ice into the test containers and this phase change material in its solid form. And so we're actually not measuring specific heat as much as we are something that's called the energy of fusion of a material. That's like the energy that it takes to turn from a liquid to a solid or a liquid to a gas. I guess those would be two different things, but from a liquid to a solid, that's the heat of fusion, not the specific heat. But since we're testing a material that we really care about the total between, I guess I'm getting a little too detailed for this live stream, but we care about the total between the melting of the material and how much heat it carries when it's already molten and trying to raise up to a higher temperature. We're looking for a total, is what I'm getting at, and I think that the specific heat equation will work for that to give us a different, well, to give us a total in addition to what it's usually used for. All right, so I did the measurement, assuming 2 cups of water. A cup, an English cup, is 236 milliliters. So I'm using 482, right? That's 236 times 2, 482, I think. No, 70. 472. Anyway, I did this on a calculator. So we're using 472 or whatever milliliters of water. And I'm trying to warm the measuring cup a little bit before I actually scoop this. I want to make sure I can get a level cup too. Fairly as level as I can. So I have doubled styrofoam cups to prevent as much heat from escaping as I can. They're mowing the lawn behind me. Can you guys hear that? Hopefully it's not too bad. The amount of times, ask any YouTuber what the most annoying thing is for them. I live near an airport, a small airport where they fly a lot of planes with, props in them. And whenever a plane flies over when I'm filming a video, they'll go right over my workshop, and it is so loud. And it can be the best take it's always the best take of the video. And they fly over, and I have to refilm the whole thing. And then my yard also backs up to a subdivision where someone's always mowing the lawn in the summer, no matter what day of the week it is. All right, so I've measured out my water into these cups. Now I'm going to put my 2 probes in here, which have been acclimating. Put those in. And let's give them a second to acclimate, and then we'll take a reading. Keep it a while, yeah. Lawns do kind of suck, but at the same time, you don't have a lot of options where I live. I mean, yeah, if you want to have ticks all through your yard with all of the diseases that they are increasingly carrying more and more often, you don't need a lawn. But yeah, I kind of need to keep the grass mowed if I want to keep ticks at bay, which I do. All right, let's see what our temperature is. All right, so these 2 cups, in scooping them out, they became 1 degree Celsius different from one another. One of them is 85.8 C, the other is 84.9. I am going to put my phase change material in the higher temperature because I want it to have a little bit harder of a challenge than the ice, to make sure that this test is done fairly or even a little bit unfairly in favor of ice over my material. And in that way we get well, the least impressive result I can get. I want to see, I want to be hard on my material and strive for accuracy more than for my own pride of having made something awesome. So the other thing I need to do before starting this test, I need to measure my ice. Okay. And then I'm going to try to drop the 2 samples in at the same time. Let's take a measurement of my bag here, and then we'll measure a sample of my ice. I don't know how many of you guys have actually done a lot of scientific stuff, especially in the realm of like home science stuff where you're using cheap equipment. But these digital scales, I end up buying digital scales in kind of in bulk because they go bad so often. But I learned a neat trick from some other YouTube video that I don't remember who made it. And it was that if you let these little digital scales, which I can't move this now, I know you guys can't see it very well with it being behind stuff, but if you let these digital scales sit at 0 for like 30 seconds or a minute before you actually use it, they'll be much more accurate, which I did not realize. I need to get, pardon me for a second, I need to get some tongs or something so that I can get my ice out of the container. Okay, scale is zeroed with this bag on it. And we are going to take a sample of ice. Oops, come on. I gotta find pieces that are small enough to fit in this bag. And again, I want to use as much as possible to make, that will make the reading more accurate because I'll have to use fewer decimal places. Come on. I also have to kind of do this fast. $12.79. $12.79 grams. And that is less than the phase change material. So the change in temperature in these cups is of course going to be less for the ice just inherently because I'm using less of it. But that doesn't matter because the equation I'll be using to calculate the change in temperature and ultimately the amount of energy that that the material carries is going to be, well, it compensates for mass. So it doesn't matter that this is less than the phase change material. Okay. All right, actually the temperatures between these two containers are evening out. And we are at 83 degrees Celsius for both of them. So starting temperature for both of these is 83 degrees Celsius. All right, so I am going to put the ice in this container. I'm going to put the PCM in that one. Let me fish it out. Actually, you know what? I just took the wrong reading, didn't I? The reading that I need to be taking, I just took the wrong reading. I'm glad I just caught that. I don't need to measure the temperature of, now wait a minute. Suddenly I'm a little bit confused at how to do this. Because we are starting off, let's see, the starting temperature here is, 0 degrees Celsius, and I'm putting it into 83 degree water. Do I need to calculate the change in the water separately from the change in this? You know what, I'm just going to do the test and I'll record both. So the temperature of this is yeah, 1 degree Celsius. So start of the tests is 1 degree Celsius. Now I'm a little confused at how to work with the equation when I'm done, but as long as I get all the data from all of this, we'll have the starting temperature of the samples, we'll have the starting temperature of the water, and then we'll have the ending temperature of the water and the samples. And from that, I should be able to calculate the specific heat, including the energy of fusion. I'm not sure exactly how that's going to work out, but I know I'll have all the data necessary to do it. Goodness, how do I reach in here? Yeah. Grab this with the tweezers, make sure it's dunked. And I want to drop these in at about the same time. All right, we're now at 81.5. So I got to re-record that. 1, 2, and cover on. (81.5 degrees C) for both. And starting temperature of the samples was 1 degree Celsius. I'm pretty confident that is the case, even though I didn't measure the samples directly. They were in there for a good, however long this stream has been going almost, which is quite a while. All right. 1 cup is slightly closer to the heat source. That's true, which would slightly heat it. Yep, you're right. Thank you for that. Actually, it's a little hot for me to move. So the cup that is close to the heat source is my phase change material. So actually, that's okay. If this warms up a little faster, well, anyways, it wouldn't give me a false positive result. It would give me a negative. Let me move this out of the way. But thank you for that warning, because you are right. So these are in doubled up foam cups, and then this block of foam is obviously quite thick, so that those should be pretty well insulated samples. Already we have dropped from, we were at 81.5 Celsius, we are down to 77.8 in this one and 79.6 in this one. This one's going to have a little worse thermal contact with the ice at first, because there was some air in the bag between the ice cubes, and so the bag in this one is floating. Let me put a little weight on this so that it has a good seal. I don't know. I'm not looking for a very exact result with this. I just want some kind of rough idea what the comparison is of this phase change material at the same temperature as ice. How those two things compare if you just, filled the same size baggie with ice instead of this stuff. How much cooling capability you could expect in comparison. I already know that the phase change material lasts way longer, but I don't actually know for sure if it actually absorbs more total heat or it just lasts longer because it absorbs heat more slowly. That's what this test is meant to detect. All right. I am thirsty. Am I familiar with how open cell reticulated foam is made? They blow it up with a hydrogen flame front. Really? That is really interesting. How do they blow it up with the flame front? Like the hydrogen causes the heating that expands the foam and causes the like little air pockets in the foam to expand in volume, or how does that work? I've been thinking about styrofoam a little bit as far as radiative cooling goes, because styrofoam is actually a very white material because of a snow scattering effect, which is the same effect I took advantage of course, in my my radiative cooling paint, making acrylic have tiny little air bubbles in it, which makes it extremely white, and it makes it an ultra white coating. And styrofoam is basically already that. The problem with styrofoam as a radiative cooler is it doesn't have a favorably emissive pigment to radiate its heat as infrared light. And it also is very insulating. And so because it's insulating, even if the surface is getting much colder, radiating its heat off into space, you're not going to feel that on the underside. It's not going to be very good at it's not going to be very good at actually, giving you BTUs or, watts per meter squared amounts of cooling on the underside of the surface because it just doesn't transfer heat. But because it's ultra white, because it's an ultra white coating, foams like styrofoam could be really interesting to experiment with for cooling purposes. So apparently for styrofoam, they put it in a sealed vacuum chamber and let some brown gas in. That's a mixture of hydrogen and oxygen in a stoichiometrically favorable form or ratio. Hydrogen permeates the entire foam and melts the cell walls once ignited. They call it zapping. That's bizarre. I'm gonna have to look into that because that sounds fun to do at home. Very inadvisable, but that's the kind of thing I like playing with. So that's interesting. I'm gonna have to let me Google that for a second. Styrofoam production. Styrene is refined into polystyrene, and then a hydrofluorocarbon agent is added. This combination is then extruded and allowed to expand under pressure until it forms a foam board. Okay, so that's extruded polystyrene, not styrofoam. Yeah, I'm sure they have all kinds of different ways of making it. Interesting. Yeah, I don't know. That's an interesting thing to know about. Thanks for that. Thanks for that idea. That's something to play with. I don't think like fish filter material. It's not regular styrofoam. Yeah. These are feet off of something. Are these off of my? The feet came off of, got hot, and I think the glue melted out of them so that they came out of my hot plate here. Are you guys here? I'm getting a ton of text messages, and I'm using my phone to film, so I don't know if that sound, I hope that sound isn't coming through. Perhaps for the next test, measure out the samples equally and hold in the freezer at a constant temp until ready to start the test. I'm concerned that we won't really know if your phase change material and the solid ice are the same starting temp. Well, we know for sure, we know absolutely for sure what the temperature of the ice was, because an ice bath, I took the temperature right off the top. An ice bath is always a consistent temperature. It should always be exactly 0 degrees Celsius, except if there's any contamination, any little bit of salt in the solution, it can be a different temperature. But it will always, the water and the ice will always be the same temperature. And so we know what temperature the ice was. It's exactly what the thermometer says it is. 1 degree Celsius or 0.8 degrees Celsius maybe, because there's a little bit of mineral content in the ice. Now the question just is, was my other sample at exactly the same temperature as the ice? And probably, it was in there for a really long time. Although when I've taken the temperature readings from my sample cooling down in my freezer at home, it goes up it goes down, at a constant angle. And then it kind of it doesn't level right off at the temperature of the freezer. It really slows once it gets close to that freezer temperature, and it takes hours and days even to really settle at the actual freezer temperature, because it's has so much heat to release over that process. And when you get to the lower differential areas, it takes a long time to do so. So the phase change material probably was not exactly at the temperature of this water, but it was close. And if anything, it was warmer than the ice water. And so again, we're doing this test in favor of the ice over the phase change material. So if the phase change material ends up being better, it had a lot of stuff stacked against it, and we can assume that it's even better than what our results show. If the ice ends up being better, then I might be a little bit disappointed and have to do this test a little bit in a little bit more of a controlled way. I don't think we did too bad here, though. I don't think we did too bad. We pre-warmed the thermal probes We let the samples sit in this ice water for a reasonably long time. I mean, I think we did pretty good by my standards, which are not the best. But in any case, if we get a better thermal capacity in the phase change in the the PCM than we do from the ice, which itself I'm getting confused because ice is also a phase change material. It changes phase into water. So calling this a PCM and this one not doesn't make sense. But if this does better than the ice at all, it will be a very, very good result. Okay. Well, so now I'm just monitoring monitoring my temp readings here, and this isn't going to tell me much really because just looking at the temperature change on here, the current temperature change is not compensated for how much of each material we have in here. So currently, I don't know if you can see that, but we have 59 degrees Celsius in this container and 71.6 in this one. So more than a 10 degrees Celsius difference. So it looks like the phase change material is doing much better than the ice currently. But of course that makes sense because we used much more of the phase change material. I was able to fit a lot more by weight into that little baggie than I was for the ice. And so it's not going to be a fair measurement until I actually plug it into the equation and figure out how to do that, because I just realized I need to, what I need to do is calculate, somehow I need to calculate the volume of or the weight of the water, which I know was 236 times 2 grams, by the temperature, the amount of change in temperature that it has. So what I'm waiting for here, I'm waiting for the temperature change to start leveling out on this thermometer, and it's still going down. Obviously, it's gonna take a while to level out, and then to actually know when we get to that leveling out point for sure. I probably will take this over to my computer, plug this in, and pull the graph out of it to see what the curves of the temperature change actually look like, and from that I'll calculate the starting temperature, the ending temperature, and we will be able to figure out which of the materials is better. Yeah. Well, this is the experiment that I really wanted to dig into in this live stream, and I don't think I'm going to be able to get the results by the end of it. So sorry about that. This is going to take probably, I should probably let these sit for a good half hour or more before I actually plug this into the computer. And then I think also I should probably agitate these containers a few times to make sure that the heat in the water is distributed evenly, because you can very easily get the warmest parts of the water to be on top and the cold on the bottom, and the temperature, therefore the temperature reading isn't accurate for the whole container. So I need to agitate these. Let's do that. Well, how do I do that? I don't know how I do that. Shaking the table. Anyways, this is going to take a little while. Do you guys have any questions about upcoming videos or current projects? You have ideas for what I could do on these live streams? Currently, I'm just letting you guys in on the live streams when I'm going to be in the workshop anyway, doing something reasonably interesting, so I can make a video out of it without being a detriment to actually getting my project out. The other thing I need to do today, of course, is to stir them at the end. Yes, I guess I could. I would want to use the smallest. In order to stir them at the end, I have to stir them with something that has the least heat capacity possible, or else, if I stir them with this, I'm going to be cooling down the water an additional amount by however much capacity this has. So I think I need to shake them with the foam pressed on top and like try to pick the whole thing up and shake it with my hand on top of the foam so that I'm not actually changing the the heat capacity of the liquid that's in the cups. Stir them with the heat probe. There you go, already acclimated. Yeah, good idea. That would work too. Did I check out the commercial cooling films that I mentioned last time? I have not yet. I've been focusing my attention on this stuff. Yeah, this has been taking a while because I've also been trying to come up with a good warm phase change material, something that could be heated with solar power and then be brought into a building to keep the building warm, or even embedded into the insulation in your roof so that your roof does not get as warm in the daytime, but then retains heat all through the night to keep the building warm at night, cold in the daytime. I've been trying to come up with materials like that, and I haven't been quite happy with those so far. I have some that kind of work, but not well enough. They're not of the appropriate temperature to actually like keep you warm, like a hot water bottle at night if you were in a cold home and you wanted to keep yourself warm. I have come up with a few that would keep a building at room temp. So that would be, yeah, anyways, I've had a lot to do with this project, so I haven't had time to test the commercial cooling films yet. I imagine I will probably work on a radiative cooling video, maybe 2 away from this current phase change material video. I'm not sure what I'll do next for certain, but the radiative cooling videos they're just difficult. It's cutting edge stuff, and I have to come up with something novel enough to be worth making a video about. And so that's difficult to do. The gelling agent that I use, CMC is a good one, carboxymethyl cellulose. This has been used in a number of papers. You can get this online. Can you see that? CMC powder. This is not what I'm using in this one, but this is what has been used in a lot of research papers to prevent the crystals from settling. As you see in this sample here, it prevents those crystals from settling out, so you don't get the layers of salt concentrations and your mixture remains uniform. This is not what I'm using. I'm using xanthan gum, which is even more common than CMC. Xanthan gum, you can get this almost at any grocery store now because it's used as like a carb-free gelling agent. So you can, if you're like on keto or something, you can use xanthan gum as a gelling agent in food to make like gravies and sauces and stuff without adding carbs. Or I guess if you're like vegetarian or vegan or something, this would probably be, you can thicken stuff without animal products or without any carbs. And so this you can find at any grocery store. Any of these natural gums. I have guar gum also, which I've used for my giant bubble mixtures. And that is, that's an awesome purpose, making giant bubbles. But you can't, that's a little harder to find in the grocery store, but I expect that it would work for this as well. So I'm using xanthan gum as my gelling agent. And I think, well, I won't give you the recipe for this in this video, but I have it, it'll be in the full video, just in case I make some changes. But primarily this is sodium sulfate, sodium chloride, table salt, and then xanthan gum. And that mixture in a particular ratio with water makes this phase change material that starts its phase transition right around room temp, and then it continues that phase transition all the way down until sub water freezing temperature. I think it has actually a pretty hard phase change at around like -16 degrees Celsius. I think it undergoes another phase change where it's the final one and you end up with a completely solid material. But everywhere from room temp all the way down to -16, in that whole range there, it's partially solidified and partially solid, just getting progressively more and more and more solid and releasing more and more heat. It's cool stuff. Yeah, trying to replicate the cooling paint I suggested. Yeah, do so. I would love to I would love to get more results. I get emails from researchers occasionally and like grad students and stuff trying to recreate my paint. A lot of people have been successful. One thing that I have realized from all the emails that I've gotten about people recreating my radiative cooling paint is that the type of acrylic matters. Acrylic windows the actual chemical composition can vary by brand, and I am using Plaskolite Optics acrylic. I think it's definitely Plaskolite, and I think Optics is like the sub name of the product. That has worked really well for me and others that I've shared that information with when they've had issues. Other brands of acrylic, some people have reached out to me and said that they never fully dissolve in acetone, and so they can't finish making their paint until it fully dissolves. And so I've diagnosed that the reason is some brands of acrylic do not dissolve. But it's really nice being able to use window acrylic for this paint, because you don't have to special order some particular molecular weight of acrylic online on some weird expensive research site, chemical supplier. You can just go down to your hardware store and get it for free, because when they cut acrylic sheets, they almost always, see, Plaskolite Optics, they almost always have these little scraps left over that are not useful for anyone's windows. And so they throw these in a trash can next to the cutting table, and you can just pull these out of their trash can and be like, can I have these? No one's gonna buy little pieces of acrylic that are too small for windows and stuff. This one's actually a little on the large side. Usually they're smaller than that. And so you can get your acrylic supply for the radiative cooling paint completely for free if you just visit a few hardware stores. So yeah, make sure you use the right acrylic. And I found that the acrylic mixture actually, with that sky cooling effect, not with the sky cooling effect, with the snow scattering effect, where you mix this in acetone and add a little bit of water, that is the primary component of the radiative cooling, making that ultra white coating. And the pigment, I've spent a long time making a really good pigment. That is actually the less important feature of the radiative cooling paint. You can get a radiative cooling coating to work just with this acrylic and the water and acetone mixture, and add in, I haven't tried really common white pigments like titanium dioxide, but I have tried amorphous off-the-shelf barium sulfate that you can get on Amazon. If you can find ultra white calcium carbonate that's not contaminated with something that makes it yellow, that will also work as the pigment in a radiative cooling coating. You don't have to go through the trouble of making the microspheres for fairly good results. And then you can go through my microsphere making process if you want the best results so far that I've been able to achieve, which is like 8 or 9 degrees below ambient temperature in direct sunlight, Fahrenheit, that is, like 6 degrees Celsius below air temperature in direct sunlight is one of my best results. And I'm going to try to improve that by tuning the micro and nanospheres to interact with particular wavelengths of infrared light at some point. That'll be something that I do probably in an upcoming video. The problem is I'm not fully confident that it will work. That was the whole point of my opal making video, is to learn how to tune micro and nanospheres to interact with particular wavelengths of light. I'm just not 100% confident that tuning the microspheres is going to work for the radiative cooling, and it's going to be a lot of effort to find out the answer to that question. And that's part of the reason why I haven't made another radiative cooling video yet, because I know it's going to be a daunting process. So I am meeting with an editor tomorrow, a local video editor, and hopefully that will speed up my video editing processes if he seems like a good fit for working on this channel. I've been able to find decent editors online, but I really want someone local, at least local enough that I can physically drive a hard drive to them with my footage on it after a long day of filming. I want to be able to not have to transfer like a terabyte of video footage over the internet. I found a local editor that looks promising, and we will see if he's a good fit for the channel. And if he is, your Patreon support, pretty much I'm going to use all of it to cover editing costs so that I can get these videos out faster. Well, not these live streams, but get my normal videos out faster and be able to work on things like the radiative cooling project more intensely without having to take a 2 or 3 week break in between videos just to be editing. So yeah, that should cut 2 or 3 weeks off of the wait time of every video. Pretty excited for that if it works out. But it's a little bit scary because editing a video like that, professional editing services for one of my videos is going to be over $1,000 per video. It's a little scary to take on that much overhead. I mean, I guess it wouldn't be necessary if I was short on money that month. I could, I could just edit my own video that time. But yeah, I think it would be worthwhile. I think that you guys would like to see videos more often. I know I would. I hate how hard it is to, when I'm thinking about video ideas, the thought that's at the forefront of my mind is this idea going to be worth a month of my life? Because that's what it takes to film and edit and upload one of these videos. And that's like on the short end these days. It's going to take a solid month, probably 2 months if 2 months if it's one of my radiative cooling projects. The longest I've ever spent on a video is probably 3 or 4 months. That's a lot of time to sink into a project. And so there's some ideas that I want to do that I just can't because I know they're not going to be worth how much time it takes to film a decent video. But if I can cut a few weeks off, that might make the difference for a lot of different ideas. All right, let me catch up on comments here. Alvaro painted with a local commercial product that is supposed to do -15°C. I assume by that you mean 15 degrees Celsius below ambient air temperature. So I think that that seems unlikely that the claim would be 15 degrees Celsius below air temperature for a commercial paint. That would be pretty revolutionary. I've not heard any paint that does that. I would imagine if it's like the paint that I've used actually to paint my barn roof, which is supposed to be a cooling paint, that it's not a paint that actually goes 15 degrees Celsius below ambient air temperature, but rather it is guaranteeing 15 degrees Celsius below your current roof temperature. That's a lot more likely than a 15 degrees C below ambient. If it actually is 15 degrees C below ambient, whatever that coating is that you found, Alvaro, I want to know what that is. Tell me the name of it so I can research it. But even in research papers, 15 degrees Celsius is the most that I've ever seen in a cutting edge research paper for a temperature differential for radiative sky cooling. And I kind of doubt that's made it into a product yet. Brand Pinturas Sur Thermostyle. Okay, I'll have to look that up. I don't know. Maybe they are maybe they do have a revolutionary product. That would be pretty amazing for 15 degrees Celsius below ambient in a commercial product. But yeah, even if not, I painted my workshop roof last summer with an ultra white paint, not a radiative cooling sub-ambient temperature paint, but it has kept my workshop just below ambient temperature during the daytime just because it cools off so much at night. And then the white coating helps it not warm up so quickly. So right now it's getting warm in my workshop, but it's still probably 5 or 10 degrees Celsius colder than it is outside. So those paints are extremely useful. Anyways, Alvaro also said that you guys are here for the science, not the editing. And that is probably true for you guys that support me on Patreon. Unfortunately, that's not necessarily true for everyone that watches my channel. And if I'm going to be funding this without some entertainment value to the videos, I would need a lot more Patreon supporters. Especially, all of my Patreon support is about to go into editing. So I will be making $0 a month if I was relying just on, those of you who really enjoy these videos just for the projects that we explore without the technical stuff, or without the, the video editing and the entertainment value. Yeah, I don't think I'm there yet. I do have to try to please the YouTube algorithm a little bit in the main channel videos, and I don't mind doing that, actually, because a big part of my channel is drawing people that are not interested in science into being interested in science. I want to show the excitement in chemistry. I myself have no degree in anything. I went to school for a few years, never intending to get a degree, just for just taking some classes that I thought would be useful for me in life. And part of the reason that I did not pursue higher education, like my brother has a master's in physics and potentially pursuing a PhD, way smarter than me. He's like 5 years younger than me, and he's a physicist. And he's who I go to physics questions, but I never excelled in school. And I think the reason is I never saw the practical application of what I was learning. Come to be who I am now as an adult, and I see that what I was learning had a ton of practical application. I just didn't know it because school, learning out of books and things, I mean, there's a place for that, and there's things that can only be learned by doing that. But they're pretty bad at teaching why this stuff is exciting, why it's exciting to learn about the natural world. And so I want to appeal to a broad audience. I want to, have my videos go viral and bring in a whole bunch of new viewers that were formerly not interested in science. My most recent video was about waterproofing fabric. So I'm getting a lot of people interested in outdoors projects coming to my channel. And then I'm going to hopefully be getting those people to be more invested, more interested in learning some of the scientific properties of the things around them. Excuse me. Yeah, so I'm on my own adventure of learning, and I want to bring a lot of people along for the ride. Yeah, there's some amazing stuff out there. One of the things that I was thinking about while I've been working on these PCMs was this problem. This problem of the salt without this gelling agent settling. Almost like the vast majority of stuff that is liquid, when it solidifies, it's heavier than its liquid state. Water is one of the things that is not like that. And it's a good thing for all of us that it isn't, or else lakes would freeze over in wintertime. The ice would fall to the bottom, exposing fresh liquid water on top, which would continue to freeze and fall to the bottom until the entire lake was frozen solid. Everywhere on Earth that gets a long freeze cycle in the winter would become uninhabitable. People, life in general, would have a lot harder time surviving if water was not less dense in its solid state than its liquid state. And hardly any materials are like that. It's pretty amazing that the chemical that we most rely on, I guess you could argue that carbon is up there too, but H2O, water, it's less dense in its solid state than its liquid, and it's because of that we can live in as wide of an environment as we can, in places where it freezes and has seasons and fish can survive, and that's amazing. It's pretty amazing to learn this stuff about science and kind of be freshly put in awe of the universe around us. It's pretty cool. Yeah, I still don't. There's a lot of stuff that I still don't understand. Latent heat, when you're talking about like heat pumps, which are all the rage these days. How basically a backwards air conditioner, those can somehow be over 400% efficient because they're not actually producing heat; they're just moving it from one place to another. I understand some of how the science of that works. I don't understand. I don't know. There's a level of 400% efficiency that I still don't understand. Like, why can you not take a heat pump to heat a boiler to then turn another heat pump to heat another boiler, and you're getting more and more efficiency with each step of the way, right? That would, obviously that's impossible due to basic thermodynamic laws. But heat pumps just like, I don't know. I haven't looked into this that much to figure out the why not of a scenario like that. And yeah, that's some of the stuff that I think about during the day that I don't bother to research yet at this point. And by the way, I am very confident that free energy machinery and stuff like that is unfortunately nonsense. Perpetual motion is another thing. Perpetual motion in perfect vacuum, electrons, things like that are kind of perpetual motion. So in a way that something like that does exist, but not in the way that people hope it would, in a way where you could draw energy from something like that. Boy, I just got real off track, didn't I? Oh, man. Well, guys, I think that, let's see, before I go, let's look at one more reading of this. We are currently at 56 degrees Celsius in this container, 63 in this one. I am going to take the idea to stir these solutions with the probes. And to do that, I'm going to have to uncover them. Let's stir these solutions. Try to stir them evenly. Still very hot. And now we're going to be losing a lot of heat energy from evaporative cooling from the... going to lose a lot of heat energy from evaporative cooling from this the lid being off. And we have slightly less water in this container, I'm noticing. So that actually is another... That is going to be another thing in favor of the ice to perform better than my my material. So when I actually do this calculation, there's a lot of things going in favor of the ice in terms of my experimental errors. That's we have less volume of water in here. We have the temperature of the ice is guaranteed to be at this at our starting temperature, where the temperature of this sample might be a little bit warmer. I forget what the other things were, but oh yeah, and then we had this the heat source over here sitting next to this container for a good long while before we started. So hopefully I still get a positive result for my my material performing better than ice, and if it does, we will really know that it performs better, because there's a lot of stuff going against it in this test. All right. What do I do? Do I wait for these to go down to all the way down to room temperature? I could potentially wait for these samples to go all the way down to room temperature and then plug the readings. I messed up. No! No, no, no. Oh, I'm sorry to shout with the microphone going. I didn't start recording on the thermometer. Oh, you guys. Oh, no. Now I'm recording. This is why videos take forever to make. Oh, no. This is bad. This is bad because if the solutions had already reached their equilibrium point with the with the ice and the phase change material before I just started the recording, which almost certainly they did reach equilibrium by now, then the temperatures of these containers have just been dropping continuously since then, and I'm not going to be able to see when that change happened without this having been recording. I need to do it over again. Oh man, there's... Yep. This is what I do here in my workshop. I mess stuff up continuously. Oh no. Oh my gosh. All right. Are you guys satisfied with how this live stream has turned out? Um, yeah. Oh, geez. Yeah, live stream 3 is incoming. I don't think that I'll repeat this test again on the live stream because I'd love to be able to talk to you guys about different topics at some point. I hope to start actually filming this video tomorrow or over the next few days. And so, yeah, that's not going to be live because I actually need to have my full attention at my other camera, and probably need my phone to Google stuff to make sure I'm I'm properly fact checking myself. Oh, okay. Yeah. Man, thank you guys for sticking with me. I really enjoy that I'm able to do a live stream like this in the middle of the day and still have some of you guys watching. And I apologize for those of you who have to catch this later when it's no longer live because you're working during the day or whatever. My wife works regular hours, and I've been trying to conform my schedule to hers so that we can actually spend some time with each other after work. And so I can't keep live streaming, at 6 p.m. or 7 p.m. when all of you would be out of work. But yeah, so getting a phone call. How do I turn that off when I'm on my on a live stream? Yeah, so probably these live streams will have to continue to be in the middle of the day, and I also apologize for not having them pre-scheduled, so more of you can jump on, with some warning. I might, I'll try to shoot to make some of these during the weekends and stuff, so more people can get on. And then also, I think what I'm going to do with these, I started a new channel. I don't like uploading these to my Shorts channel necessarily because the reason I moved Shorts off of my main channel to begin with is because I didn't like that I was getting a bunch of Shorts subscribers on that channel who weren't really interested in watching my long form videos to begin with. I don't want the same thing to happen on this channel with a mixture of live stream, people who are interested in live streams and Shorts. And so I have another channel. I'll have to post it on Patreon. I tried to start posting this live stream to that channel today, but apparently you need 50 subscribers on a new channel in order to start a live stream. So I'll post that channel onto Patreon. Hopefully I can get some people to subscribe to that one, and then I can live stream from there. And these live streams, I think what I'll do is I'll keep them private for Patreon members only while they're live. And then at a later date, I will publish them so that everyone can benefit a little bit from the Q&A here. I don't like locking too much stuff behind doors for patrons because I appreciate those of you who support me even though you're not wealthy or anything like that. Thank you very much for that. But I know some people are not some of you are maybe not very wealthy and you're still supporting me on Patreon. For that, I want to thank you, and I also want to be cautious. I don't want to ask anything from anyone who is already pressed for money. That's not how I want to get support, if you need more help than I do. But anyways, I know there's people that cannot support me through Patreon that would also love to if they had the money. And so I want to be able to post things like these live streams eventually publicly so that people like that, it's not locked behind a door of a certain threshold of wealth. I want everyone to be able to benefit from what we talk about. But I think the benefit for patrons will be that you actually get to see these things live and get to ask questions and things. And maybe occasionally I'll do live streams for everybody, but those will be, fewer and far between. But yeah, it's worked out. I've enjoyed doing these from my cell phone as I am right now, except for the the phone calls that come in. I guess I could just turn the phone on silent. But anyways, yeah, it's worked out well. Yeah, yeah, it's great. It is great to be able to do the live streams spontaneously when I have something that I can demonstrate on camera. Otherwise, I'd just be sitting here rambling about all the, the books I've been reading. I've really gotten into LibriVox, the free audiobook organization. It's like LibriVox.org, and they have a YouTube channel. And so I've been listening to a bunch of old books. I don't know, should I bring up the books I've been reading? I mean, they're a little controversial, but I don't think they should be. Yeah, I don't know. So one of the books that I listened to recently, Uncle Tom's Cabin. Uh, I know almost everyone has heard of this book, and you've heard of like Uncle Tom being used derogatorily. I wanted to read the book or listen to the book on audio, and it was awesome. It was so good. One of the most important books in American history. It convinced. It was part of convincing Lincoln of the evils of slavery, and it's got some stereotypes in it that are not. It was written in like 1850 or something like that by a white woman, and so there's bound to be some, stereotypes of the time that leak through. No one can be perfect in their time, but it was an awesome book, and I highly recommend it. Maybe I'll do some more book recommendations and stuff when I jump on these live streams. I've also been listening to a lot of philosophy recently that is less excellent, but I want to know about it. I'm interested in a whole lot of stuff, and the science stuff is really what you see in the main channel videos. One of the things I like about going live is I get to talk about other interests. So I don't know. I guess I always had another test I had to do with this anyway, because the rock over here, the piece of cement, I better get the water boiling again to run this test over. And this time I think I will run both thermometers at the same time, and we're going to try to get a result with the concrete and the PCM versus the ice, all recorded this time, and hopefully I'll have results in the main channel video. Anyway, I want to thank you guys so much for watching. I think I am about to end this live stream. Let me just look down here and see if there's any more comments I want to reply to. Yeah, the cooling stuff. I am doing a lot of cooling projects recently. I think that it's just obviously helpful to people. I think that being able to keep yourself cool. I like the PCM stuff that I've been doing. The radiative cooling is, of course, a lot more flashy, and it has the potential to do all kinds of cool stuff for the world, to have really good radiative cooling coatings. But the PCM stuff is simple. And I think that it can help a lot of people now. It can, like I mentioned earlier, I've had people email me asking for things that they could use, paramedics, things that they could use to save people from heat stroke when it's too hot out and too humid out, to rely on other means of rapidly cooling someone down. And PCMs are perfect for that. This material would be excellent at cooling someone down. I had another person, this was a while ago, for my during my Starlight videos, asking if I could come up with a fire blanket, something that fire persons, whatever, could cover themselves with in forest fires, or when they're overwhelmed by fire, to actually stay protected for a more significant amount of time than the current options. PCMs are also a viable option for that. The trouble is they're a little bit heavy. It's, you'd be carrying a blanket around that's saturated with a half gallon or a liter and a half or something of liquid, and so that's inherently kind of heavy. But it could be very worthwhile to have in a fire truck or something that's going into the brush to keep people safe. So yeah, I feel like this is an important video, and it's worked out way better than I thought with how long this stuff has kept me cool through the day in my testing of it, without even needing to throw it in the freezer. But it works even better if you do. It stays colder than ice, longer than ice, if you throw it in the freezer. And then it maintains sub-ambient temperatures for hours and hours and hours after that. So anyway, I hope you guys are excited for the full channel video. I'm thinking I will try to get that out. It kind of depends on how I like this editor and how quickly I can start working with him, if he's a good fit. Hopefully I can get the video out in maybe 2 or 3 weeks. If I have to edit it myself, it's going to be another month still. Anyways, I need to get to thinking about how I'm going to actually film this and present it in a way that sells it for what it is. shows what it's good for. And yeah, so that's what I need to do with the rest of the day. Thank you all for being with me here in the live stream. Thanks for supporting me on Patreon. I really appreciate it. It's unbelievable how meaningful that's been to me. Thank you, all of you. To be able to even think of the option of hiring an editor is only because Patreon is the only consistent income that I have. To be upfront, I make more money off sponsorships and stuff. My wife still has to work because we can't afford health insurance on what I make. I can make more off of sponsorships and things like that, but not consistently. I don't know when my next sponsor paycheck is coming unless I sign agreements to produce so many videos in a year or whatever. And I don't like doing that. The sponsors that I have, I'm very careful that I actually like them. But it's still, it's at the whims of companies whether or not I make a living. And you guys have turned that around through Patreon support. So thank you so much. I have said I was ending this video about 5 times now. So this is it, guys. Thank you. I will see you I will see you once I make 400 more mistakes. And probably they will not come up in the main channel video, but I will have many more mistakes to report in the next live stream. See you guys. Thanks for being with me.